I repeat what I said, that as strange as it may seem, is the first time that I introduced Maria Esteban to the seminar. And so it is a true pleasure to do it because of the deep friendship that we have and the long collaboration over the years. So Maria will talk about the subject that has Louis involved. In fact, it's about sharp symmetry breaking result for Caffarelli-Nirenberg inequality. So please, Maria.
Thank you very much. It's a big pleasure to be here to celebrate Louis' 19 years and also for the other prize that we already celebrated, but we can celebrate many times together. And I want to thank Gabriela and Daniele for the work they have done to organize this nice workshop. Okay, so I'm going to talk about this subject. Maybe some people here have already heard me speaking about this subject because I've been working on symmetry issues for Caffarelli-Nirenberg inequalities for some years. Actually, I started working on these inequalities through Gabriela. Gabriela came to Paris and she wanted to study the link between Onofre inequalities in dimension 2 and actually generalized Onofre inequalities and Caffarelli-Nirenberg inequalities in dimension 2, and so this is when I started working on this subject. So over the years, I collaborated with different people on this subject, and we've made progress little by little using different methods. And the work I'm going to talk about is a collaboration with Jean Dolbeau and Michael Loss, and it's final because now we have a new method that proves the result in the optimal and optimal result about symmetry and symmetry breaking. Okay, so well, I think many people here know probably the inequalities. So these are the Caffarelli-Nirenberg inequalities, and this is a class of them. So as you see, it's like a Sobolev inequality. You bound the LP norm of a function b in Rb by the L2 norm of the gradient, but with weights. So you have some weights here, and you have three parameters in these inequalities. You have A in the denominator here, you have B and PB. And in order to have a scale invariance, you have a relation between these three parameters. So once you give, for example, B and A, that is a dimension, then P is defined. So you have actually two free parameters. And already in the initial paper of Caffarelli-Nirenberg, it was proved that in order to have this inequality, you have to make some assumptions on the parameters, and in particular, B has to be between A and A plus 1 in dimension 3 and larger, and in dimension 2 you have to exclude B equal to A. And also you have to exclude, and actually we'll see later why, you have to exclude the case when A is exactly equal to dimension minus 2 divided by 2. Okay? So these inequalities are scale invariant. You see that they are invariant by rotation because everything here is invariant by rotation. The space, the operator gradient, and also the weights. And it's an interesting question to understand when you look at minima and extremal functions for these inequalities, whether they reproduce or not the symmetry of the problem. Okay? This question of symmetry and symmetry breaking is very important in many areas. For example, in physics, chemistry, etc., there are many areas in which you have a problem which has is invariant at a group of symmetries, and you want to understand whether the best solutions or the minimal energy solutions in those problems reproduce the symmetry of the problem. And it's not always the case, and this is a question that is very important in many applications. So we chose just to, I will choose to speak about these inequalities, but what I am going to say could be said about other kinds of inequalities. Okay, so just let me make some remarks about the inequalities. And when you look at the set of parameters in which the inequality takes place, you can look at extremes. Extremes, so one extreme is when B approaches A plus 1, and this is a case in which P approaches 2 when you look at this formula. And the other extreme is when B becomes close to A, and in this case, P goes to the critical Sobolev exponent. So actually, you think in terms of P, these inequalities naturally are for cases in which P is between 2 and the critical Sobolev exponent. And also, let me say that when you look at these inequalities and you define CAB as the best constant, these inequalities are absolutely equivalent to a minimization problem, which is defining 1 over the base constant is equal to the minimum, the infimum, of an energy functional, which is the quotient of the right-hand side divided by the left-hand side. Okay? So often when I will speak about extremal functions here, I will speak about minimizers. So it's equivalent, okay? So minimizers for this minimization problem are equivalent to extremal functions for this inequalities. Okay. So the question of symmetry, as I was saying, is an important question. So what is it? So if I define CAD as the base constant here, I can define as CAD star the base constant, but only when I am thinking about radially symmetric functions. Okay? And of course, by definition, it's easy to see that, it's immediate to see that C star is less than or equal C. Okay? And in the case of radial symmetry, we know everything. We know that up to a scalar multiplication and dilation, the optimal radial function in these inequalities is given by this expression. So this is, everything is known in the radial case, and since you know the optimizers in the radial case, of course you know the value for C star AD. And even you know it explicitly because you can compute it with gamma functions, etc. Okay, so the question is whether optimality here, first the question is whether when you have such an inequality you have existence of optimizers, and the second one is whether you have symmetry or not for the optimizers. Okay, and a naive idea that was, for example, a naive idea that many people had maybe 20 years ago is that when you have a problem which has invariances, then the minimizers should exhibit the same invariances. But we know now in many cases this is not the case. Okay, so let me explain some history about this problem. So about the existence, let's say about the symmetry, existence of minimizers in the whole strip, in the interior of the strip, B between A and B plus 1, was proved actually by Katrina and Wang. And about symmetry, there are many people who are working this problem for different values of the parameters. Give me just, let me some names. For example, when A is positive, when B is larger or equal to 2, when A is positive, there are many people who have worked in this for this problem. So, for example, when you are at this point here, you have the Sobolev inequality. When you are here on this line, you have Hardy inequality. So all these inequalities are very well known, and different people have worked on them for various of the parameters. So just in the summary of the symmetry results, when you are in this green region, so when A is positive, A is this number which is here in the denominator. So when A is positive, you have always symmetry for the minimizers. So you can use either symmetrization results, symmetrization methods, or moving planes also, and you can prove that in this area the minimizers or the extremal functions for the inequalities are always radially symmetric. And I have written some names that are attached to these results for different cases. Now, when A is negative, the situation becomes more difficult because you can't apply moving plane methods, for example. Symmetrization results only in the case B larger than 2. So the case A less than 2 is more difficult when you try to analyze the symmetry properties. And indeed, actually, Katrina and Wang, and then proved something about symmetry breaking, and this result was completed by Felix Schneider. And well, the two things together, what they proved is that there is a black area here, this black area, there is a curve, this curve is explicitly written here, so that in this set, you have symmetry breaking for the minimizers. Okay? So you have a set of parameters for which the extremal functions are not radially symmetric. And how you can see it? Well, the proof is a little bit technical, but the idea is very simple. What they did, both Katrina and Wang this work was completed by Felix Schneider, what they did was to look at the set in which the radial minimizers are global minimizers in the set of radial functions. But if you look at them in the set of all functions, they are not local minima. They are saddle points. And of course, if you are a saddle point, you can't be a global minimum. Okay? So that's how Katrina Wang and Felix Schneider proved that in this set, the radial minimizers are saddle points. And this curve is the curve in which you look at the Hessian, you have exactly 0 as eigenvalue. So you have in this black set, you have a negative eigenvalue, and over the curve you have exactly 1 if you look at the second value. Okay. So of course, once you have this symmetry breaking result and you have the symmetry in this green area, you see that there are a lot of values of the parameters, all this white region, in which you don't know what to do. Because in this white region, the radial minimizers are stable, they are local minima, so maybe they can be global minima. So there were some results at the beginning, some perturbative results. First for A negative, but very close to this line, the A equal to 0. It was a work by Lin and Wang, in which they proved that you have symmetry in this red region. And then later, with Gabriela and Dolbo and Loos, we proved that you are near this line, so you are near the Hardy inequality, you have also symmetry, okay? So we started to see that in this white region, actually, wherever we look by perturbative results, you had symmetry. So the conjecture was whether in the whole white area we have symmetry. So the conjecture is whether when the radial minimizers are stable, they are local minimizers, whether they are global or not. And the conjecture was that yes, it was the case. Okay, so I'm going to prove that actually today. So as I said before, we have been, I mean, a lot of people have been working on this problem, and every time we try to find an idea to prove the symmetry here, but it wasn't easy, so every time we made some progress. And I think the last progress before the one I'm going to tell you about today was a result that we proved with Dolbo and Loos in 2011, in which we found an explicit curve, which is this curve here. It's explicit, I counted it out as explicit. And we proved that above this curve, we had always symmetry. And we had a tiny region between this curve and the Felius-Naden curve in which we didn't know what to do. To prove this, we already proved, we used a very, I would say, a strange method which was linked to leaf-theory inequalities. Leaf-theory inequalities are inequalities that are very, very well known in spectral theory, so for people who work with linear operators. But here we are working with nonlinear operators, and still we saw that using leaf-theory inequalities, we were able to prove symmetry almost in the whole set. And I think one of the few persons who have understood that leaf-theory can play a role also in nonlinear inequalities is Gabriela. So many people have proved. Okay, so we had this result from 2011, and from 2011 we're trying still from time to time. Every time we met with Michael Loos, we were discussing with John, we were trying still to fill the gap and find a method that solved the problem. The question is that the question is not so easy because actually at some point with Jean Dolbo we looked just as an exercise to look at inequalities which already were also in the Caffarelli-Nirenberg initial paper. And these inequalities are a little bit more complicated than the previous ones. They contain an extra interpolation. So what you have here is interpolation between the L2 norm of the function and the L2 norm of the gradient. You have different weights in the denominator, and you have an interpolation parameter which is theta, which is between 0 and 1. These inequalities were already in the initial paper of Caffarelli-Nirenberg. And what we saw, I mean, these inequalities, you can look at them exactly the same way. Well, they are more complicated. But there was a paper of Del Pino, Dolbo, Filipas, and Tertitas in which they analyzed completely the radial symmetry case for these inequalities. And actually, in a paper that we proved that we published with Dolbo, Tarantello, and Tertitas in 2011 also, we saw that for thetas which are small enough, in these inequalities, you can have symmetry breaking, even in cases in which the radial minimizer is stable, is a local minimum. So we found this by a little bit contradiction in some sense. I mean, we saw that we had symmetry, so this was counterintuitive because we were looking for the other result. Okay, so we found these strange examples, and it was always for thetas less than when we compute numerically things, small enough. So we never approached 1. It was always, in all cases for all p's and lambdas, the theta was never above 0.75. And we ran actually very precise numerical computations, which are more bold, myself, and we saw that we understood why we have this strange symmetry breaking result. I don't have time to speak about that today. I prefer to concentrate in the result, the final result for the case theta equal to 1. So what we have proved now with Dolbeault laws is that when theta equal to 1, this strange phenomenon that we found for theta small doesn't happen, and actually the conjecture is true. For theta equal to 1, whenever the radial minimizer is stable, it's a local minimum, it's going to be a global minimum. Okay? But this is a very sensitive problem, because you see that you change the theta, then you don't have that result. Okay. So just to say a little bit, many of the results that we prove regarding the Nirenberg inequalities are done through a change of variable, which is very useful. It's Enden-Follett-Klein transformation, which transforms the space RD, the Euclidean space RD, into the cylinder R cross the unit sphere in RD. And the change of variables is the following one. For every x in RD, you take the log of the modulus of x, you call it S. So of course S lives in R, because modulus of x can be less than 1 or larger than 1. And then you define omega as the angle you see is x over modulus of x, it lives in the unit sphere. And then for a function v, which is defined on RD, you define a function in the cylinder by phi s omega equal x modulus of x to the minus a times v of x. Okay, this change of variables is very nice. It was already in previous papers, it was the invention of ours. And the nice thing about the change of variables is that the Nirenberg inequalities written in these variables are equivalent to these inequalities, these Gagliardo-Sobolev inequalities, let's say, on the cylinder, where you just see that the LP norm is bounded by a constant times H1 norm. Okay? So, so you got rid of the weights. That's the nice thing. The Euler-Lagrange equations are local. You don't have any more the weights. Okay, so here you see that you have a new, when you make this change of variables, you have a parameter here which appears lambda, which is lambda is 1/4 of d minus 2 minus 2a to the square. And as I told you, in these inequalities, there are two parameters which are free. The other ones you can find from them. And so when you look at this inequality, you see that in the context of the cylinder, well, the right parameters to use is lambda p, because this is the one which appears explicitly in the inequality. Okay? And here in this inequality, you can see why before I was avoiding the case in which a was equal to d minus 2 over 2. Because you have a equal to d minus 2 over 2, lambda is going to be 0. And of course, if p is so critical, there is no way that you control LP only with the gradient. Okay, you need the L2 also. So you need that lambda is strictly larger than 0. Okay, so these inequalities are absolutely equivalent to the Nirenberg inequalities, and of course you have a related minimization problem, which is just minimizing this h1 norm to the square divided by the LP norm to the square. It's the same thing. The only thing is that now you don't have weights. So you gain something because you got rid of the weights, you lose something. In the cylinder you don't have a scaling variance. So you trade a scaling variance by getting rid of the weights. Okay. So just to show that this looks like a very easy problem, because looking at the extremals of these inequalities, when you look at the Euler-Lagrange equations of the minimization problem, is equivalent to looking for Laurent-Stake solutions of this equation in the cylinder. So you see, this is the easiest semi-linear equation in the cylinder. Okay, of the power here, so very easy equation. And the question of symmetry is now the symmetry, how the symmetry, the radial symmetry in RD translates in the cylinder. So radial symmetry translates in saying that the functions don't depend on the angles, depend only on the longitudinal variable in the cylinder. So you In the cylinder you have the S variable, and then you have the angles. Okay, so radial symmetry in RD translates in the cylinder by saying that you have only dependent on the R variable in the cylinder. So our question is whether when the radial minimizes, so the positive solutions of this equation are stable in the general set of functions, whether they are the only solution or positive solutions of this equation. You want to speak of PDEs instead of speaking of minimization problems. Okay, so so we prove that. We prove actually that we have symmetry always when we have stability. Yeah.
Sorry, what does the second line mean? That the solution which are experiments for inequalities depend actually only on the azimuthal angle. So they don't.
Yeah, sorry. So this is a partial symmetry resolved by Willen and Smith. They proved actually that you have the minimizers. Maybe they are not symmetric, but they have partial symmetry. And the partial symmetry is that they depend only on one of the angles. So you have symmetry breaking. The functions will depend on S and on the azimuthal angle on the sphere. Only one angle intervenes. So it's a 2D problem. So this was proved by Willen and Smith in the general setting.
You mean, for example, only one of the Euler coordinates on the sphere?
Yeah. The azimuthal angle actually. In polar coordinates. Okay, so we have proved this result. So I'm going to, we've been working in this problem, as I said, for several years, and we have used different methods, and we knew that in order to prove a sharp result, we had to find another method, because all the methods we had used didn't work, okay? Didn't give the optimal result. So recently, actually, we have proved this 1 month ago, and it started some months ago. We saw something, we made a different change of variables that put us in the right path to prove the optimal result. So what we observed actually is the following. You can make a change of variables which is just scaling in RD. So I come back to RD, okay, so the Caffarelli universe in RD. And you can make a scale, just a change of a scale. Okay, you write a new variable R, you pass to R alpha, and you choose the right alpha. And when you choose the right alpha and the right parameters, you can see that these inequalities are equivalent to another kind of inequality in RD, which are these ones. And they look a lot like Sobolev inequality. So I'm going to spend some time to explain this. So you make this change of variables, you define n a number by this formula, okay? And you define everything in order to get rid of the weights again. But in RD, not in the system. And you can do it. And what you have is the following. You have kind of Sobolev inequality. Now it's real Sobolev. You don't have L2 norm. You have only the D. Okay? And D is not exactly the gradient. It's like the gradient, but with this constant alpha in front of the radial derivative. Okay? And then you have a measure. The measure is not the usual Lebesgue measure. You get a measure which is Rn minus 1 dr d omega. So this looks like the Lebesgue measure, but not in RD, but in Rn. So by this change of variables, you choose well n and alpha. You write like a Sobolev inequality, but with something that is not a gradient, but is almost like a gradient. And you have a measure that makes the inequality a little bit straight. But you observe that this looks like you can choose the n so that t, this parameter, the exponent, is equal to n over n minus 2. So in some sense, if we were in Rn, this would be the critical Sobolev inequality. But we are not in RD, we are in Rn. So it's like Sobolev inequality behaves, the scale, I mean, you look at only the radial part, this behaves at critical Sobolev. But you are not in Rn, you are in RD. So it's strange. And also, it looks like Sobolev inequality in Rn, but n, there is no reason why it's an integer. So it's a dimension between quotes. It's really an integer. But when we saw that, we remembered something that is in a book by Bakri and Ledoux and Gentil, in which they speak about Sobolev inequalities in fractional dimensions. So we thought about it a little bit, okay? And then that put us in the path of trying to apply methods that are related to Bakri-Emery methods, that are related to entropy methods. Okay? Entropy methods have been used recently, in the recent years, very much to find optimal constants in inequalities, to find the optimizers, and to find also optimized versions of the inequalities. Okay? So when we saw this, we thought that maybe there was a chance to use some kind of entropy method to prove the result. And we tried and it worked. Okay, so I'm going to explain that. Okay, so I repeat, this is equivalent to Caffarelli-Nirenberg inequality. If you look at the radial part, it scales like critical Sobolev in Rn, but with this alpha there. Okay, good. No, so we tried, so we see now that the parameters are not maybe a lambda and p, but now when you look at this inequality, you prefer to choose alpha and p, because these are the things that are explicit in the inequality. So we try to compute what is the critical alpha, the alpha which corresponds to symmetry breaking in the Frey-Schneider regime. So the alpha which is critical is this one, okay, we computed it. So what we want to prove is that whenever alpha is less than this number, we have symmetry. Okay? So this is the theory we prove. You have d larger than 2, and you have alpha less than or equal alpha fs. Optimality is achieved by radial functions. And this is optimal because we know by the result of Frey-Schneider that if alpha is strictly larger than this number, then you have symmetry weight. So this is optimal result, this theory. Okay? So how we prove it? Well, just some notation. So we have this gradient here. So it's a strange gradient. So we can define, once we have a gradient, we can define the corresponding Laplacian, which is just defined in the usual way. Okay, so it looks like a Laplacian, only we have this alpha square in front. Of course, we have the usual integration by parts. And I mean, we have to be careful. This integration by parts works with the measure, which was the measure r n to the minus 1, even if we are in Rd, so this is not a Lebesgue measure. But with respect to this measure, we have this integration by parts property, okay? And so, what we want to do now is the following. We want to define a flow, a nonlinear flow, so that we have, how to say, our energy functional is a Lyapunov function along this flow. So let me define things. So let me define U as WP. Okay? W was the function you define Rd, and P was the exponent 2n over n minus 2. So we take U equal to WP. So the integral in Rd of WP is the integral in U of Rd, so it's the mass of U with respect to this measure, always this measure, which is not a Lebesgue measure. And then we can compute also the kind of, the Sobolev norm Q1. So the integral of d of omega, well, d is this operator with the alpha inside. And we can see that in the new variables u, this integral can be written as the integral of u times dp squared. And p is this function here, so it's a power of u. Okay. And we write it in this way because this is something that is really, which is called the Fisher information when you work with entropy, etc., etc. So we chose to write things in a way which is classical in this kind of methods. Okay, so what we want now to do in some sense is to minimize this. We wanted to minimize this Sobolev integral with respect to the function of w, for example, that you can normalize normal d. So now, in the context of U, what we want is to minimize I of U, this Fisher information, with respect to the functions which have mass equal to 1. So now the constraint is the mass of U. Okay, so now once we are here, this looks very much as many things that people in the entropy community have done. What we have done is to define, to look for a flow, a nonlinear flow. So what means a flow? A flow is just a parabolic equation, it's a nonlinear equation, it's a fast diffusion equation because n is less than 1. So you have like ut equal to Laplacian un. When n is less than 1, you see, it's this number, so it's fast diffusion. And the strategy is the following. We want to prove that along this flow, this energy function, this Fisher information is decreasing. okay, when we keep constant the mass. And then we want to prove that when you have not only, because you have for every function, we will prove that it is decreasing. When we have that is equal to 0, you have an initial value for which is constant along the flow. The energy is constant along the flow. Then we will prove that these beams being radially symmetric. So this is the strategy. Okay, so we have now a functional. We have a constraint, which is the mass. We keep it equal to 1, for example. And we want to prove that this functional is a diagonal function along this flow. So we want to prove that for this particular flow, I of u is decreasing along the flow. You take the initial value, and then you see that along the flow you are decreasing, and you want to prove that being constant, and when I is constant, then it means Rx. Okay, so we have to prove this. Actually, this flow, we don't want to spend time studying it because it's a not very nice flow to study. So you will see that the real proof will not go along this line. But this is the intuition. Yeah. This is what we follow. Okay? Okay, so the mass is conserved. That you can see that this flow conserved, the mass is conserved along the flow. And then you can see the following thing. You define, I make my final definitions. So I already defined first the pressure function. The pressure function is just this power of u. Then I have a flow for u. Sorry, I have a flow for u. I can write it for p. So it's useful to have it. So this is the parabolic equation for p. It's a little bit more complicated, you see it. And then I still have here my Fisher function. Okay. And I define this function, which looks very strange. But why I define this function is because we can prove a proposition which says the following. When you look formally at this, when you look at the derivative along the flow of this functional, you see that this is equal to minus a positive constant times kappa of this function. So this is just a computation. There is nothing deep about it. You compute. Actually, there is something deep. Because when you compute this, I mean, you can do it formally, but you have a lot of integration by parts to be done. And the integration by parts are not easy near 0 and near infinity because you have terms that have to vanish. And for this, you need to know how the possible solutions behave near 0 or infinity. So the main work in the proof of this proposition is not the computation. The computation is long, it takes several pages. The main thing is to study the regularity properties near the origin and infinity, and it takes a lot of work. So this is the painful part of the proof. But anyway, we managed to prove that in dimension d2 or larger, along the flow, this functional is equal to a negative constant times k. Then the second proposition is that when alpha is less than alpha fs, exactly in this range of parameters, kappa is non-negative. Okay? So we see already that when alpha is less than alpha fs, the energy, this energy function decreases along the flow. Okay? So we have something that is like a diagonal function. It decreases. The third proposition is to prove that if u0 is a critical point or a minimizer of our minimization problem, then we have that kappa is equal to 0 at this point. Why? This is easy to explain. If you have a critical point of I when you fix the mass, you know that I prime of u0 is 0.
Sorry, say that again, you know what?
When you have a critical point of I, you know that I prime is going to be 0. Okay, so 0 will be equal to I prime multiplied by something. But this thing is actually the derivative of the functional at time equal to 0, because the flow was u dot equal to L un. Okay, so if you start at the function u0, which is a critical point of I keeping the mass constant, you have that this is equal to 0 because I prime is 0, because you have a critical point. And then you see, you understand well, that this is just the derivative of is the instant derivative at time equal to 0 of the functional along the flow. So we don't need to study the flow. We just need to look at instantaneously when when you differentiate in the direction given by the flow.
Yes.
So the flow tells us in which direction we have to look at the variation. So we are just doing the flow to get this intuition. Okay? So, but then we use the first proposition, and we know that this guy is equal to minus constant times kappa p0. So what we see is that if I prime of u0 is equal to 0, so you have a critical point, not only a minimizer, critical point, then 0 is equal to kappa p0, because this constant is what it is. Okay? So this is the third proposition. And the final proposition is that when alpha is less than alpha fs, kappa p equal to 0, okay, because we see here, we put together proposition 2 and proposition 3, kappa p is equal to 0, and then we analyze this function, kappa p, and we see that this is going to tell us that p is independent on the angles, radial symmetry, and actually we have a precise shape of p. Okay, so these are the 4 steps of the proof. So, I don't know if you have any question about this is the strategy. So now I'm going to explain a little bit some of the ideas. You want some question about the strategy? Okay. So I think, these are the 4 steps. So now I will not say anything about proposition 1, because I told you it's just calculation, integration by parts, and making sure that the boundary terms don't bother you. Okay, so this is just a very lengthy computation, several pages of computation, but you have it. And you see a kappa of p which looks complicated, but you will see that it's complicated, but it's very nice. Okay, so now I'm going to show you how nice it is. Kappa of p can be written, actually, as this function, which was actually what was in the previous thing, multiplied by p to the 1 minus n, and the measure integrate, okay? So we are going to study the integrand. We are going to study this guy, locally, point once. So we are going to look at the integrand, and when we look at the integrand, we spend some time, and this is also several pages of computation. We knew what we're looking for. We're looking for kappa being positive. Positive means, or you look for, you have like a matrix, you want to see that this corresponds to a quadratic, to a quadratic form that is positive. So either the whole matrix is positive, or you manage to write blocks of positive matrices in the matrix, okay? So we're trying to prove that this guy was the sum of the squares. And that's what we proved. We proved that kappa of p is a strange expression. When you spend time computing, you can write as the sum of this square here, plus this square here, plus another guy who is here, and which looks awful if you look at it. Okay, it looks like an awful quantity. But if you know something about differential geometry, you see that this quantity makes a lot of sense. Because this is a quantity which appears in the Wagner-Lisenovich-Weizsäcker formula that is related to Ricci curvature and all these things. So this quantity, when we saw it, we understood what we had. So you have that this integrand is the sum of 2 squares plus this guy. This guy we are going to analyze. We are going to use this Wagner-Lisenovich-Weizsäcker formula to see that actually this guy is larger than this quantity times the gradient p squared plus a positive number gradient p4. So you see that we have 2 squares already, and now we see that this guy is also positive if lambda is less than lambda fs. Here is when enters the condition, the assumption. When lambda is less than alpha fs, this guy is positive, and so the integral is positive because we got the sum of 2 squares plus this. And this is going to be positive if lambda is less than lambda fs. Okay, so here is where we see the assumption, where it intervenes. Okay. Now you have just this is a little remark. So this we did for spherical cylinders. You can actually generalize this to general cylinders, where you don't have just the spherical one, but you have a general manifold, compact manifold, you multiply it by r, and so you have same kind of thing. So what we prove actually is going to be more general than Raffaelli-Nirenberg. We are going to prove things for all the geometries. It could be interesting in differential geometry. Okay? So now what we have proved is the following. So what we have proved is that you have b larger than 2, p between 2 and the critical exponent. We exclude so whatever. Then we have proved that we have symmetry because we have all these propositions, and we have proved when lambda is less than lambda fs, we have that the kappa is positive. And then we identify what we do in the end is the following thing. We look now again at kappa of P0. We know that for critical point, kappa of P0 is equal to 0 by proposition 3, I think it was. And then we see, as I showed before, that this kappa P is larger than this square. I drop the other one because it's still positive. And then I have these numbers. Now, if alpha is less than alpha fs, everybody here is positive. So I have the sum of three things positive, which are equal to 0. So it means that everybody has to be equal to 0 individually. But if I look at this case, if I look at this term, for alpha strictly less than alpha fs, I have already here that the gradient of P0 is going to be 0. Sorry, and I forgot to say something important. These gradients are only the angular gradients. When I had derivatives in S, it was comma. Okay? So these are just angular gradients. So if alpha is strictly less than alpha fs, I have here something that is equal to 0. So it tells me that gradient P0 is equal to 0, so I have no dependence on the angles. If alpha is equal to alpha fs, this term drops. Okay? It drops, but I have still this guy here. And this guy, as I said before, these constants are positive. And so I have again angular gradient of P0 to the 4. So I have that the angular gradient is equal to 0. So I see that whenever alpha is less than or equal to alpha fs, gradient of P0, the angular gradient is equal to 0. So I have radial symmetry because I have no dependence on the angles. And then I finish the proof by saying, okay, I already don't know that I have no angular dependence. And then I look at this term. So if I have no angular dependence, this is the angular Laplace-Beltrami operation on the manifold. This guy drops, and I have that P second derivative minus first derivative divided by R is equal to 0. And that identifies me P0 as constant times the constant times R squared. And I have finished the proof. Okay? So by using this flow, this nonlinear flow, I see that the energy function that I am minimizing is decreasing along the flow, and I see that any critical point is stable for the flow. And that allows me to say that the derivative along the flow has to be 0, because it's stable, okay? And then I can identify what it means being stable. Being stable is meaning that the derivative of the function of the flow is equal to 0, and then I use this positivity to prove that actually the P0 doesn't depend on the angles. So I have radial symmetry, and even this term allows me to identify exactly how the solution has to be. And so I finish with this. This finishes the proof, but it's more interesting than proving symmetry for Caffarelli collinear. I have used, you noticed some slides ago, I finished speaking about minimizers. I started to speak about critical points. So what we have proved is not only symmetry for the minimizers, for the streamers of Caffarelli Nirenberg. We have proved that every positive solution of the Euler-Lagrange equations is equal to this. Okay? So we have proved rigidity. Rigidity means that you have uniqueness. We have proved actually is that the equation, the Euler-Lagrange equation, have only one positive solution. The radial ones are the only ones. There is no other positive solutions that are not regular. Okay, so this result is much more than proving symmetry for the minimizers of Caffarelli, the streamers of Caffarelli Nirenberg equalities. It's a rigidity result for the corresponding Euler-Lagrange equation. So thank you very much.
To me, since we started the project a long time ago, so I'm very impressed indeed when you find the solutions. But we take questions.
The earlier results were you?
Wait, maybe I will ask you.
The earlier results were striking of symmetry was known, did the U change sign?
No, positive.
No, always positive.
Positive, yes.
Always positive.
Yeah, so in the Fehlschneider region, the minimizers have broken symmetry, but they are positive. Actually, you don't know them explicitly, but we computed them numerically, so you see very well how they behave. And you can see, for example, when the lambda parameter goes to infinity, the functions concentrate at a point, and you can compute them numerically. You know them. So they are positive. Yes.
Other questions?
So the key point is one transparency where you introduce this new measure and this function u, the function u and p.
Yeah.
That
Yeah.
p is like power of u, right?
Yeah. Yeah.
And do you have like a receipt to say how do I find them?
Once we show that the inequalities in this change of this scaling, we have like a Sobolev inequality, even if the measure was on the right one and the gradient was not the right one. For those kind of inequalities, we know that this kind of fat diffusion flows are the right thing.
Yeah, this yes.
And then the U is the natural variable for this entropy methods. And the pressure also is efficient information. I mean, all this we knew. I mean, we didn't know if it would work or not, but we knew that it was the path we had to follow.
But everything comes from taking R to the alpha, right?
Yes.
This is the key point.
Yes, and we never saw it before.
No. And maybe U also to a power, U to a lower power.
No.
Yeah, it's a power, it's W to the power. I mean, I can even say an anecdote, because I think it's really an anecdote, you know. I was, I mean, some people know here, I was very sick this year, I was in the hospital for months. And then when I came out, I was feeling not very well. And Jean Dolboy is somebody who pushes you to work all the time, you know. So he's
We know.
So he came to the hospital, he wanted me to work, and I was telling him, I cannot, I have no energy. But then I went home, and he kept coming to visit me. And then I said, well, maybe at some point I will go back to this computation. So he said, no, it's too involved, Maria. You know what you can do? He was trying to push me to do something, because I was really lazy, but I was weak. And then he said, you know, you remember this thing we saw in Bakri, Ledoux, Gentil book, in their book, about these Sobolev inequalities with non-integer dimensions and all that? I said, yes, I remember. And he said, why don't you try to see if there is a way of, it was just like that. And then we looked at that more intensely, let's say. It was my first exercise about after being sick. And then we were together, you know, he was trying to push me to work. And then we saw that, and then we understood we had to try. We didn't know if it would work or not.
Yeah.
We had to try that. But it's a consequence of being sick. It's not bad.
There's a conservation in life, you know. The bad with the good. Okay. Thank you, Maria, very much.